Okay, so now we're going to find the slope of the tangent at a value of a function that isn't polynomial, that is a radical. And so the method here is different. We can't expand the way we do with a polynomial, so it kind of limits what we can do in terms of that kind of operation. But we know now, based on what we've done before, that with radicals, we can rationalize them. And that is a helpful tool that's going to let us look at this presented in a different way so that we can take the limit. So I came up with this function here. Now I'm looking for the slope of the tangent when x is 1. And so we set up our difference quotient using an a value of 1, which makes a plus h 1 plus h. So our first job again is to set this up so that these actually become y values, which means I have to take 1 plus h and plug it into the function where we see x. So this becomes the square root of 2 times 1 plus h plus 3. And then we do it again with the x value of 1. We plug it in 2 times 1 plus 3 all over h. And so we can clean this up a little bit. So let's do that first. So what's going to happen here is this is going to become 2 plus 3, making 5, and this 2 gets distributed to the h as well. So I'm going to write this as 2h plus 5. And over here I get 2 plus 3, which is the square root of 5 also, all over h. So right now, again, I'm done in terms of expanding and simplifying. I can't go any further. So what I'm going to do is I'm going to apply the conjugate. I'm going to multiply by the conjugate here so that I can get rid of these roots on the numerator and see if that helps us simplify our expression here at all. So I'm going to multiply by the conjugate of the numerator, which means I leave both terms the same, but in between both terms I switch the sign. So this is going to become plus. And like every fraction, whatever I do to the numerator, I have to do to the denominator. So we multiply by the conjugate on the denominator as well. So then in my next line, I'm going to simplify the numerator. So the nice thing about the conjugate is what I've really created here is a difference of squares. It's the factored form of a difference of squares. So when I go back and I expand it, I'm not going to get a crazy trinomial. I'm going to get the square of the first term minus the square of the last term, and there is no middle term because these signs are opposites. That's all I'm going to see. Anything else will cancel out, for lack of a better word. So I'm going to get 2h plus 5 2h plus 5 squared. So all that's going to happen there is that the 2h plus 5 isn't going to have a root on it anymore, minus root 5 squared, which also won't have a root on it anymore, all over, and I'm not going to expand the denominator. I'm going to leave the h. I'm going to link it by multiplication to the root 2h plus 5 plus root 5, but I'm not actually going to expand it yet because I want to see what happens on this numerator. So in my next line, I can tidy up that numerator a little bit. 5 minus 5 is gone. I'm going to have a 2h as my numerator, all over h times 2h plus 5 under the root plus root 5. And now, because I left this linked by multiplication, I can divide h by h and simplify this. So there's no longer that single h hanging out. And even though you might think this doesn't look any nicer, what's happened now for us is that it's gotten rid of the problem with the 0 denominator. We don't have that issue anymore. I can plug in 0 here for h, and I'm not going to get an undefined slope. So because it's okay to plug in the 0, I'm going to do that now. So I'm not going to write limit anymore. I'm going to evaluate the limit at 0. So remember how to add your radicals. This 2 times 0 is gone, so all we get is root 5 plus root 5. And when I add root 5 plus root 5, that means I have 2 root 5s together, which actually allows us to simplify our fraction a little bit more. 2 divided by 2 means the slope of my tangent at 1 is going to be 1 over root 5. And we're done. So multiplying by the conjugate so that we can evaluate for our radical functions.